It's great. So let's get started, everyone. So welcome back. We are going to talk today about random variables. So discrete random variables, which is kind of we'll do continuous random variables later, which is kind of like a little bit trickier in various ways. So we'll start with discrete random variables. These are kind of a really important concept within probability, and I think can take a while to wrap your head around a little bit. And so we're gonna not rush through them. In other classes I often teach, I have to kind of start at the beginning of the semester by like reviewing kind of random variables at the start and kind of rush through them. And I think if people haven't seen them or they forgot about them, that's always confusing. So we're gonna kind of make sure we go through them kind of gradually to understand. It's kind of a tricky concept, though I think if you're kind of had some computer science, it's a little bit easier because you're used to thinking about kind of variables more than just like if have just taken other courses in math before. So before we get into this, let's just recall everything on the schedule. I think I've been pretty good this semester about keeping all the links up to date, but not perfect. There have been a couple times I realized afterwards I'd broken some of the links on the website. Please tell me if I have. I think like I try and like today's lecture should be linked off of here. For instance, talked about the discrete random variables. I noticed I'd had like a lecture versus lectures folder, and I had mixed those up. So if you see a broken link, please, so tell me about that, because that'll be useful for you to find. And if the link's broken, then it'll be a lot harder to find it. Quiz 3 is today. So we'll stop a little bit, kind of with 15 minutes left in the lecture today. So you have time to take the quiz. We structured quiz 3, so it's not going to be on the discrete random variables yet. Quiz 4 will kind of cover this sort of stuff. So it'll be more on Bayes rule and kind of the other parts are probably like independence that's leading up to that. And then, yeah, so homework 2, was it? Yeah, so homework 2 is due on Tuesday next week. Great. So if you haven't printed out homework 2 yet, I've got a few more copies up here in front. Come up after class to come. So grab them if you haven't done that already. I think most of you have gotten them and have gotten started on that. Again, if not, remember, this is when a lot of people who have questions about it go seek the help hours. And so we've kind of structured them. So most of the help hours every week are between now and when the assignment is due. And recall, these have been slightly updating due to some scheduling conflicts, mostly room changes sort of things. But so check here, there are a bunch between now and when the when the assignment is due. And then including I'll be available after class today. So great. Yeah, generally, you could ask me quick questions before class, but I kind of have a complicated kind of setup here. So it's not a great time to ask me too many questions. I'll be kind of distracted. All right. Great. So discrete random variables. So what is a random variable? I'm gonna, on the next slide, I'm gonna write down the definition for this, but kind of want to think about it just a little bit before then, before I try to write down like a definition. So kind of implicitly, like if you've like programmed before, a useful way to think about this is you have a variable that you in your code, right? That's in a program that's going to run, right? And that variable probably has a yeah, if you're using like a language that has like a type, right? So who knows the difference between typed and untyped languages? That makes sense? Or no, don't heard of, have you, who's not heard of typed versus untyped languages? All right, so if you're just getting started, a typed language is one where if you have a variable, you have to declare what type of variable that is. So if I have a variable x, right, it has to be like an integer, or it could be like a binary value. An integer actually means only some like finite number of integers, right? Or it can be a more continuous value, which you have as like a float or a double, or it could be a string, right? So think of this type as like your sample space. Okay, there's a set of possible outcomes with probability, but you don't know what that variable is going to be, right? When you run a program, something will get assigned into that variable. But what if the program somehow uses randomness in order to do it? The program says, go and flip a coin or go and like roll a dice, right? There's a function in the language you can call that gives you a random value in some way, right? So you're going to put a random value into that variable, right? And what we'll see, and we'll do this within our kind of so starting next week, for specific types of random variables, there are these built-in functions to do this. But it could be kind of any function, right? You write a function in your code, the output is the random variable, and there's some random process, right? So this is how you think of like a random variable from a computer science perspective. There's some random function that you write that uses randomness somehow, and it outputs something within that type, inside the sample space. Okay. Okay, so let's just preface this. It's a variable, but you don't know the outcome of it yet because there's a function that's going to run, or because you're going to observe something about the world. Most a statistics class, probability class, not for computer scientists and engineers, might describe it as, I'm going to observe something about the world. That seems much more messy to me. That's actually how like a data scientist would view like a random variable. They're going to make an observation about the world, where a computer scientist might have a randomized algorithm. When you make an observation about the world, it fits into a form again because you're going to record that observation. And so that observation, through how you record it, I might do a checkbox, I might write down a number. That's ultimately what the end value of this random variable is, right? But I haven't observed it yet. I'm going to flip a coin. It's going to be head or tails, but I haven't flipped it yet, so I don't know what it's going to be. Okay, so let's write down something more formal. Random variable. Okay, so to define this, so I gave you this to plant your head in what's actually going on here, but a random variable x, right? So a random variable x, is going to be function from sample space, right, omega, to the to the real values. Okay, so when I write this blackboard bold R, this R with the two lines, parallel lines on those vertical ones, that's the set of real values, right? So it's going to be, so we'll actually look at things that are more restrictive than the real values for now. But think of it as, the output is just going to be a number, okay? So this is the definition of a random variable, which is much less, I think, intuitive. We would write this, if you've taken a kind of a discrete math class or other math classes, you would think of writing a function. You say x is going to have the domain of the function is going to be the sample space, and then you put an arrow, and the range of the function, the output of it, is going to be the real numbers. Okay. So yeah, so this seems kind of, what I'm doing is I'm taking a sample space, which we've talked about, like heads or tails of a coin, rolling of a dice. I'm drawing a red or a blue ball out of, some bins, some urns, or I'm drawing a sequence of like red and blue balls, or I've got a deck of cards and I'm drawing one card out of the deck, right? Or I'm dealing out 5 cards out of the deck because you're playing poker, right? The sample space are the sets of 5 cards, and I'm mapping those to numbers. Okay. This will turn out to be kind of necessary that they're numbers. What's actually most important is that this is the domain of the function, and so this is the range. And what'll be really important is that the range, you can actually have a comparison operator. You need to be able to say less than or greater than. Okay, but we could think of kind of the range of a function. Remember, the sample space is the domain, and so this is the range of the function. And you think of the function as for everything in the the domain, it's going to have exactly one value, right? So for something in the domain, you map up, and it is giving you something in the range, right? This is a function definition, right? Now we're going to look at simpler functions initially, right? So I just want to define this. We'll go through some examples. And yeah, good. What? Oh, yeah, okay, right. So it's so the range, okay, so technically the range is going to be a subset of the real numbers, right? So, but we'll think of like so it's what the output could be without knowing what the function is, right? Once I know the function, it's actually going to have a fixed set of possible outcomes in this, in this range, right? But I'll often abuse this notation. Say it's actually anything it might map to without knowing what the function is. And we'll look at more kind of restrictions of this, but I just kind of want to give you this picture. And what's important is we're going to want to be able to sort stuff in the output. Okay. In a bunch of the stuff I do, you actually have random variables where the output is more than just real numbers, but in some of the researchy stuff. But for this class, all we need to think about, and is just the output is just going to be the real numbers here. Okay. Okay, so let's go through a really simple example. Okay, so if I have, if I have a coin, right, then and I flip the coin, the sample space is just going to be heads or tails. Okay, and we're going to talk about just today, this is kind of a continuous picture, a continuous way of thinking about it, and this definition will hold for continuous thing. But we're going to talk about discrete functions, right? And discrete functions you can write down as a table. Okay, so I can think of the sample space is in a table, and the possible sample space are heads and tails. Okay, and then I'm going to put the output, I'm going to have a random variable x. Okay, and if it is heads, then I'm going to get a value 0. And if it is tails, I'm going to get a value of 1. Okay, those are elements of real numbers. They happen to be also, integers, happen also to be binary values. Okay, but this is actually a pretty common situation. If I want to, for instance, if I want to check if a coin is a fair coin, then I might do a lot of flips, and I might add up all the ones and zeros, and I expect the value to be about. And if I divide by the number of flips, I expect it to be about 0.5 if it's a fair coin. And that would be something we'll talk about later in the semester, how you would kind of evaluate if that works. But this is kind of a pretty common sort of random variable. To make this a little bit more complicated, now let's say that I flip a coin twice. Okay, so now my sample space is going to be heads, 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 tails, tails, heads, and tails, tails. Right, so now the sample space is 4 things, and I can write this down in a table function again. Right, so now I have heads, 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 tails, tails, heads, tails, tails, right? And so now I could say, well, the output of this might be that 0, 0, 1, so 5, okay? This would be kind of a random variable as well, right? Random variable x. Okay, so I could say, well, my random variable x is going to map from, I'm going to flip a coin twice, and maybe these are representing the amount of, if we're playing a game, and I'm going to flip a coin twice, and I say, I'm going to pay you $1 if I get tails, heads, right? I'm going to $1 if I do tails, heads, tails, tails, you're going to get, like $5, but you're going to get $0 if I do heads, tails, or heads, heads. So would you pay $1 to play this game, right? That's like a sort of like a question you could ask, right? So we can start thinking about these things where we're turning a random sort of like a possible like random event into a number that you can compare. Okay, so I want to turn the sample space into a value. Okay, I don't know what's going to happen though, right? So that value, I know it's going to be 0, 0, 1, or 5. Okay, but I don't know what it's going to be until I actually do the experiment. But we can reason about it before the experiment happens. Okay, and so probability with the random variables allows us to reason about things before experiments happen. Okay, or before observations happen, or before we run a piece of code, we can analyze what's possible outcomes going to be. Okay. All right, so it's some sort of output feature that I can compare from the sample space. Okay, I haven't talked about probability yet, but I could, we'll think about for now equally likely probability. I could say, if these are equally likely outcomes for flipping 2 coins, what's the probability I get like $1, right? So I could ask this question, what's the probability that x is equal to 1? If these are equally likely outcomes, it's a fair coin. So 1/4, yeah. And then I could say probability, what's the probability that x is equal to 0? So 1/2, right? Because there are 2 outcomes that would give that. And then I could say what's the probability that x is less than 2. I can do comparison operations on it. So 3/4, right? The first 3 outcomes out of 4, it has this. So this is 3/4 is the probability. Right? So now I can talk about probabilistic outcomes of these random variables. Okay? Okay, so this allows me to start talking about quantities instead of just the events in the sample space, just the subsets. Yeah. Yeah, right. So this is why it's kind of confusing, because the definition is the sample space is somehow endowed with the probability. For most of the time, we'll be talking about, for a while, it's equally likely outcomes on the sample space. But then it's typical to write, and this is why the notation and the concept of random variable is useful, is I can do comparison operations with the variable as if it was a scalar, but I can put it into I can look at the probability that, so this is true, right? So the random variable, okay, so the random variable is a function from the sample space to like the real values. But I'm going to treat it like it's actually a variable I don't know the outcome of. So I can write these comparison operations. I don't know anything about this, doesn't tell me anything about the probability itself, right? So this definition just maps from the sample space to the outcomes. So I can look at the sample space. It just describes like this table here, right? It just describes the mapping. Okay, the probability, that's the probability is with respect to the sample space, and I can use comparison operators to write things compactly. Does that answer your question, or did I miss some aspect of it?
Well, I guess
So think of it as a function that doesn't have an input, right? So it's actually, so it's kind of like x of, like, right, of some input, right? You think of a function as mapping from some input, which is the sample space, right? But I don't actually, this is kind of implicit, right? So I'm kind of not writing this down. And what goes into that, the sample space is kind of, is kind of uncertain anyways, right? It's some random draw from the sample space. And so that you typically write it without this kind of, x of the input sort of like notation, you just say x, right? So it is a function, but we don't use, when we write it, we don't want to write that notation down. That will make it look really confusing. It'll be useful to just pretend it's like a variable that we haven't like solved for yet in algebra. So it technically is a function, but we're kind of not going to, we're often not going to think of it that way. We're going to think of it as just something we don't know the value of yet. And what the value will take will be described by a combination of, how it maps from the sample space and what's often an equally likely kind of probability on the sample space. Okay, so we're going to kind of, so you're probably going to mostly forget this technical definition after today. It's not really, I find it not really that helpful. That's why I prefaced it with something else, and then we're going into other ways to kind of how to use it will be more intuitive than this actual definition of a function. So I apologize, but like if someone asks you what's a random variable and it actually is a function from the sample space to these outcomes, but you treat it just like a variable that hasn't been assigned yet. Okay. Yeah.
So a random variable is like a translation of a sample space of equally likely outcomes into a set of values whose probability can be combined numerically and are not necessarily like.
Right. Well, the sample space doesn't need to be equally likely. We'll stick with those sort of examples for now. This will get a little bit more convoluted with the continuous random variable. Well, I'll try and bring it back where usually there's a way you can think of things like they're equally likely if you transform what you say is the sample space. So all right, so we're gonna go through this with some examples, and I think how to use them will be more clear. And for now, everything for the next probably for this lecture, everything will be equally likely. Actually, starting on Tuesday, we're gonna kind of skip a shorthand and things are not gonna be equally likely. But there's a way to imagine it that way, but it's convenient not to have that restriction. Okay, but for now, just think of the sample spaces as equally likely. Yeah. Yes, right. Yes, that's exactly what's going on. A random variable gives a number to each event to each possible outcome in the sample space. The events can be sets of possible outcomes. Okay, but it gives a number to every possible outcome in the sample space. Right. So here there are 4 possible outcomes. I'm going to go through a little bit more complex example where they're going to be there'll be 36 possible outcomes, and we'll see it's going to give a number exactly onto each of those. Yeah. All right. Okay, let's go through this next example. I'm going to roll 2 die, right? So D1, the outcomes are 1, 2, 3, 4, 5, 6, and D2, again, 1, 2, 3, 4, 5, 6. Okay, so I can think of the sample space, right? The sample space is going to be 1, 1, 1, 2, up to 1, 6, 2, 1, 2, 1, 2, 2, and so on up to 6, 6. I think it's more useful to think of it as a table. You have D1, let's see, and D2. These are going to take on values 1, 2, 3, 4, 5, and 6, and 1, 2, 3, 4, 5, and 6. Okay, so we can think of this as a table. And there are going to be 36 possible outcomes here, right? For instance, this particular cell is 2, 5, right? Die 1, or 5, 2. This is 5, 2. Die 1 rolled a 5, and die 2 rolled a 2. Okay? Okay, and now my random variable, okay, my random, so variable is going to be, I'm going to call this S, and this will be the sum of values of the 2 die. Okay. Okay, so it's going to be the sum of the values of the 2 die. Okay, and so now I can write these values in this table here, right? So this value is 2. 1 and a 1 is 2. 1 and a 2 is 3. 1 and a 3 is 4. This is 5, 6, 7. Actually, you're going to get 7, 7, 7, 7, 6, 6, 6, 6, 5, 5, 5, 4, 4, 3 was 8. Right, so this describes, there's a 36 size, 36 sample space, and I've got the and I've got a value for each of the outcomes of the sample space, right? So you think of, you've got the domain of the sample space, and the function is the function is coming up out, and there's a value. You can think of it as a height value if you want to, but it's, it's a number for each of the elements of the sample space. And S is a random variable that maps from that sample space to that number. Okay? Okay, so we can then, with this example, right, we can ask questions such as, let's see, so you can say, yeah, so I can write something like set notation, S is equal to A, right? So this is going to give me, do I use S here? All right, so let's say that, so that, yeah, so let's say S is equal to A, right? This notation with the curly brackets, right, is writing a set. This is going to be equal to all of the elements, which equal to some A, right? So if I say, so A would be a value, right? So it could be like the value 5. So if I say S is equal to 5, maybe I'll use 4 because my S's and 5s look a little similar. Okay, so this will be equal to the set 3, 1, 2, 2, and 1, 3. Yeah. No, A here is like a restriction to the random variable. Okay, so A here is saying A is like 4, right? This is in general, I could pick some value A, but let's say it's 4, right? If for S is equal to 4, what are the elements of the sample space where S is equal to 4? So this notation is saying, what is that set, right? The elements where S is equal to 4 of the sample space are 3, 1, 2, 2, and 1, 3, right? They are exactly 3, 1, 2, 2, and 1, 3, right? So it's exactly these objects is where S is equal to 4. And also I just highlighted all the 4s, but I can also think of them as the elements of the sample space, right? With the D1 and the D2 labels. Okay. Right, so in general, yeah, so in general, S is equal to A is defined as the elements of the sample space such that, or S of A is S of that element is equal to A. Okay, so the elements of the sample space, right? The sample space is this setup here, right? So the elements of the sample space, so this is a lowercase omega, right? It looks like a W, right? So I put that into the function, and if it returns A, then that's one element of the set, right? So this is why I can talk about this probability, right? I look at the set of things in the sample space that map to it, where the probability I got one of those elements in the sample space. If they're equally likely, then I just count the probability, right? So I can then write the probability of S equal to 4. Well, that's going to be the size of S equals to A divided by the size of the sample space, if they're equally likely, right? And so this is equal to 3 out of 36. Okay, so if they're equally likely, then equal to A, right? Then I can just count the number of elements, the number of things in the sample space that take on that value and divide by the size of the sample space. Right, so the probability that I roll 2 die and the sum of them is equal to 4. Yeah, this should be 4 in this example. Oops. S is equal to 4, right? The probability that S is equal to 4 is going to be 1/12, right? Right, is 1/12 they're equal to 4. But that's different for like S is equal to 6, right? So S is equal to 6 is going to be 5 out of 36. Okay? So it allows me to talk about these kind of different outcomes pretty easily, right? It's a powerful notation for doing that. All right, so this kind of makes sense. All right, so I'm going to give you an example here to work out to try again. Okay, so let's again roll 2, so die. Okay, so say D, it helps D1 and so D2. They're both, so fair die, they both have, so 6 sides, right? Okay, and I'm going to say that some random variable X, so random variable, I'll just say RV, X is going to be equal to the product of the outcomes of the outcomes of D1 and D2. Okay, so I'm going to roll them. I'm going to take the product of them, multiplying them instead of adding them. Okay, and what I want you to work out is the probability that of X is equal to A for A equals to 3, 4, let's say 12, and let's say so 13. All right, so go and kind of work this out. Breakout rooms, I'm a bit short-staffed today. Let me see if I can do this. All right, and once you do that, you can talk with your neighbor and kind of do this if you want. So if you think you have the answers, check with your neighbors, see if you have about the same thing. So let's see how you did. So what did people get for the probability that x is equal to 3? So 2 out of 36. And so can you say how you came to that answer? Yeah, so the only ways the set x is equal to 3 was only 1 times 3 and 3 times 1. Those are the only answers. And we already knew from the previous example I did that there were 36 points in the sample space. So the size of that set, which is 2 out of 36, right? Okay, great. So probability x is equal to 4. Anyone have an answer? 2 out, so let's see, I have 2 out of 18, 1 out of 18, and 1 out of 12. 1 out of 12 might be old. Yeah, what do you say? So 1/9? Yeah, so you have 1. So 9th, how did you get that? Yeah, I think that looks like, I think you calculated, if you showed your work, I would give you full credit, but you had 1 and 4, 2 and 2, and 4 and 1. So that's 3. That's 3 out of 36, which is 1/12. Just a little calculation error, which is fine. That's why you should show your work, and then you can still get credit. But make sure you work through all those calculations. So yeah, so 1/12, right? Okay, great. And then probability of x equals to 12. Yeah.
This is.
There are 4 and 36 possibilities, right? Right. So for 1/12, you could get, let's see, 3 and 4, and 4 and 3, and 2 and 6, and 6 and 2. And those are the only ways you can get 12, right? Okay, so that's 4 out of 36, which is 1/9. Okay, and then for a probability of x equals, so 13, so 0, right? This is 0 because there's no ways to get x equals to 13. Okay, there are going to be some values that you can get. You could get x equal to 14, these larger values, but there are these. It doesn't have to be everything is positive. A bunch of events that can't happen are going to end up with the probability of 0, right? So okay, great. Okay, good. So this is kind of how like a random variable works. You're kind of converting these outcomes into these values, and it's simple example, just taking the sum or the product of things on dice, right? We will, as we'll see, you can model more complicated sort of like phenomena with this, and kind of the next week's Tuesday's lecture, we'll see kind of some very common random variables that are more complicated than like the equally likely sort of things. Okay. Another reason random variables are so useful is because we can write down things like a probability, so density function. Okay. This would be abbreviated, so PDF, just like the document format, but this is probably, so density function. This one, so came first, the PDF, the portable document format, I think, probably came after this, an older concept. In the book, this is often called the probability, so mass function, and PMF. And this distinction in notation can be a little bit confusing, and it's led to, we'll see in R, the naming conventions follow something similar to this, but in most of like machine learning and data science, they use probability, so density function, which is what I'm more so familiar with. So that's what I'll be saying in this class. Okay, so the probability density function, and all this is a function, okay, from the real values to 0, 1. Okay. At least for discrete random variables, it's going to be between real values to 0, 1. We'll always use, I'll try and always use lowercase f for the probability density function. And typically this corresponds with a particular random variable. So if I say f of x, so sub x, is the PDF for the random variable x. Okay. And so all this is f of x of a is going to be equal to the probability that x is equal to a. Okay, so these are the things we were calculating in these last few examples, right? This is another function, but this time I'm mapping to the probability. Okay, so I'm mapping to a probability now from x. So I just want to think of the if I'm looking at the outcomes of the random variable, I'm saying what's the probability of that outcome? That's the PDF. Okay, so if I were to think of, for instance, this S, remember this is the sum of two die, then this took on values, let's say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so it's a function, right? And so this value of the outcome, right? This would be f of s. Okay, so this outcome is going to be for 0, it's 0 at 0, 0 at 1, at 2, it's going to be a small value, right? This is going to be 1 out of 36. There's only one outcome for this. At 3, this sum of two things, this is twice as high. That's going to be 2 out of 36, right? So 4, there are 3 possible ways. 5 more possible ways, 6, 7 has the most ways, and then it's going to come back down. If I draw this right here. Okay. And only 2 ways for 12. Okay. Well, not exactly perfect, but okay. I will get these perfect when I do some stuff with R. Well, if I have a computer do it, then it will draw it totally precisely, and that will be the power of kind of using, programming languages like R, right? So I think of a function, and it's 0, right? It's 0 for a bunch of these places. For like 0 and 1, there's no way I can get the sum to be 0, no way I can get the sum to be 1 or 13. But for all these other values between 1 and 12, I have some value, which is the probability, right, that it hits that value. Okay? So now, so it's similar to the random variable. That is mapping from the sample space to the value. And the PDF is saying, from the value, what's the probability I got that value? Okay, and these are kind of useful ways to kind of access and kind of shorthand notation to deal with these sort of random variables, right? Okay, so I can also, alternatively for the, for S equals the sum of 2 die, I could write this as S, right, as the, of this value A, right? And this would be F of S of A. Okay, so I could write 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right, as the function. So, and it's discrete, so I can write this as a table, and the outcome of the function is 1 here, is 1 out of 36. For 2, for 3, it's 2 out of 36. For 4, 3 out of 36. 5, 4 out of 36. 6, 5 out of 36. 6 out of 36. And so on here, right? Okay, so I can map this function from the possible kind of values that the random variable can take to their probability. Okay. So, and these are in order, right? So when you have a table like this, you're going to write them in order, and we'll see what is kind of useful to write here as the order is this next example. So I will come back here after I define this next concept, which is the cumulative density function. So this would be called the CDF. Okay. This is sometimes called the cumulative distribution function. I guess that might be what's called in the book, but it's the same abbreviation. So the CDF here. And for this, we will use an uppercase F. So F of A is going to be, I'll always use the uppercase F, and F of X is going to be the CDF for random variable X. Okay, in particular, F of X of A is going to be the probability that X is less than or equal to A. Okay, so it's accumulating the mass, starting from the smallest value up until A. So this one is, it's a simple kind of a transformation of the PDF. And this is sometimes very useful to think about and talk about. Actually, if you're doing computation on like a discrete, so probably density function, this is super convenient to actually store the CDF instead of the PDF. So an example, so let's go back through this example here. Okay, so now I'm going to add another column into this table. It's a function, again, from the same, so domain here to f of s of a. Now it's uppercase F, okay? And now I can write the CDF values here, right? So for 1, right, this is 0, this is 0. For 2, it's 1 out of 36, that's the same. For 3, that's 3 out of 36. For 4, that's going to be 6 out of 36. Let's see, 10 out of 36, 15 out of 36, 21 out of 36, 26, 33, right? This is equal to 1. And for any value 13 here, it's going to be equal to 1. Okay? So the CDF, it's going to be a function from from the real values, which are the outcome of the random variable, again to 0 and 1. So this is also a probability, and probabilities need to always be between 0 and 1. But this has the nice property that it's always increasing. Okay, so it's always increasing. And so anything less than 2 is going to be 0, right? So f of s of, I can ask, say, like 1.5. This makes sense. Just ask. The answer to this would be so 0, right? I can do f of s of 5.7, and this would be, read it off the table there, if you can read my handwriting. Okay, let's see, 5 is 1036, and 6 is 1536, right? So those are kind of the relevant things here. So what is the CDF, the cumulative density function at 5.7? Yeah, so it's still 10 out of 36, right? Because this is the probability that x is less than or equal to 5.7. Well, I know what the value is at 5, I know it at 6, but there's no probability happens between 5 and 6, right? So I can just round down to the next smallest one, and that's the right value. It's a step function, right? So it's a monotonic step function. If I were to draw it on here, it's kind of going to be going up like this, right? It's going all over the place here, but it's gonna be this step function here, and we'll draw these a little bit more carefully, kind of in R later. But it's between 0 and 1, and it eventually reaches the value of 1, right? So for the domain here, the PDF is going to kind of look like this. It's going to look something like this, where the CDF is going to be a step function, right? And it's going to start from 0, and it's going to make it always makes it all the way up to 1 here. Okay, the PDF doesn't typically make it up to 1. That would only happen all the things happen at the exact same spot. All the density was at the exact same spot. Then it would only be at 1 there for discrete random variables. But for the CDF, it always makes it up to 1 and then it stays there, right? So if I ask something in between, right? So I ask a question at like 5.7, well, I go up here and I get the step function that happened at some actual discrete value, right? It's the same as that step function. Okay. Okay, so one cool thing about this is if I ask a question, what's the probability of something happened between 5 and 10, right? Probability that the value of S was between 5 and 10, including 5 and 10 itself, right? Or actually, let's say, yeah, but so between 5 and 10, how would I answer this quickly in like a what's an algorithm to answer this quickly? Yeah.
So we take and subtract it by fs of 4.
Yeah. Right. So I take these two numbers, I just subtract them, and I get everything in between. Right. I don't have to go through the list and add all this stuff up. I can just index into those two things and subtract them, and that gives me everything in between. So it's kind of a convenient format to store your data in as well, right? So it often makes for fast algorithms. You can look up stuff like these differences very quickly. So this is also kind of a cool kind of algorithms trick. So if you take an algorithms class, hopefully they'll ask you a question that this is the trick to the fast answer. Okay. Great. Okay, good. So this is what I wanted to cover today. This was, I think, a lot for a short lecture. We'll kind of review this stuff on Tuesday, and then we're going to go through a bunch of kind of very common probability distributions that we'll write them as the random variables and their PDFs, and they're things where you kind of don't have equally likely like outcomes in those cases. And so they'll be a little bit more interesting, but common cases, and we'll analyze those. All right, so the quiz is now open, and we'll start the quiet time in here in 5 minutes, and I'll be available for questions after 5 o'clock, or questions about the quiz until then. Okay. What are you? So sorry for those in the chat. I missed my TA Anna wasn't here today. Okay, great. Looks like you guys helped answer each other's questions. So great. Good job.